Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's weekly contest, shortest distance after road addition queries 2. The problem is different from the second problem of the contest because second problem doesn't have one particular constraint, and this constraint make this third problem a way more different than what the second problem was. So the solution to this will not work for second problem, but second problem the constraints are very small, so the brute force solution that we discuss in the current problem would work in the second problem as well. So with that, let's get started. The problem states that you're given an integer n and a 2D integer array queries. There are n cities numbered from 0 to n minus 1, and initially there is a unidirectional road from city I to city I plus 1 for all the i's. Now each query is denoted by two integers ui and vi, which represent there is a new unidirectional road from city ui to city vi. Now after each query you need to find out the length of the shortest path from city 0 to city n minus 1. You are given some constraint, we'll come to that. You need to finally return an answer array which contain the shortest path between 0 to n minus 1 after every query is applied, right? So let's take an example. Let's say n is 5, which means there are 5 cities 0, 1, 2, 3, 4. Each of them are connected, like city I is connected to city I plus 1 initially, and we have 3 queries, right? Or in other words, 3 additional road. After each additional road we need to figure out the shortest path between 0 and n minus 1. So let's start with 2 comma 4. So it says that there is a new additional road from 2 to 4. Now what's shortest path now? Shortest path is 0 to 1, 1 to 2, 2 to 4. So length of the shortest path is 3. Now let's say you added one more road 0 to 2. So if you add this road as well, the shortest path between 0 and 4 would be 0 to 2 and 2 to 4, which is of length 2. Now finally they are saying let's add one more road between 0 and 4. If you do so, you can literally take this particular route and reach 4 in just one length, and hence the answer here is 1. So hope the problem statement is clear. Now how to solve this? The brute force way would be, okay, I want the shortest path between two nodes, right? And I can consider this entire thing as a graph. Now after a new addition, let's say there's a new path that's get added here. So after a new addition, I will say, okay, I will apply any shortest path algorithm, let's say Dijkstra, and figure out what's the shortest path between node 0 and node n minus 1, right? And I will do it for every iteration. So I have this particular graph. Now in the next iteration, I will have one more edge somewhere, let's say from here to here. So I will again apply Dijkstra from 0 to n minus 1, and this Dijkstra iteration would be independent of the previous iteration, right? So overall we are applying Dijkstra n number of times or q number of times. So if there are q queries, we will be applying Dijkstra q number of times, and each iteration of Dijkstra will take us n log n time. It's u log e, v log e, but here number of vertices and number of edges are almost equivalent. So this will be the overall time complexity of our brute force algorithm. Now this surely will not work for the third problem because number of queries is 10 power 5, n is also 10 power 5, so this will not work. But this could pass for the second problem easily because number of queries is 500 and n is also 500, so this would work here, right? Now coming back here, we need to optimize this. Now how to optimize this? First of all, you can't remove this queue. You need to answer something for every query, so this queue can't be removed. This is the only thing that you can remove, that is figuring out how to find out the shortest path between two nodes efficiently is something you need to work on, right? Now this n log n is the fastest one which you can get with Dijkstra, right? You need, if you want to optimize this, you don't, basically in some way you are saying that I don't want to apply any shortest path algorithm, because if you apply shortest path algorithm, you need to iterate over at least all the edges once, right? So if you iterate over all these ones, the best case you can get is order n. Like you not have log n, but you still have order n, and q into n is also not feasible here. So in essence, what we are saying is we are not allowed to apply shortest path algorithm at all, right? And we have to solve that without applying shortest path algorithm. And if this is feasible, it means you are somehow asking for, without applying shortest path algorithm, tell me the shortest distance between two nodes, which to be honest is very hard. And hence they have given this extra constraint to make this graph looks like, to make the structure of the graph a bit more different than the usual graph, and hence without applying shortest path algorithm itself we can solve this, right? So this is the key to this problem. So let's focus on that. Again, if you know about how to solve the problem without shortest path with the same constraint, I am very happy to learn that. You can post that in the comment section below, and I can make another video on it if needed. So coming back to this problem, we have this particular constraint, right? And this makes the graph a bit more different. So what this says is, there are, if there's two queries, let's say I and j, right? Those two edges will never satisfy this equation, right? Notice it doesn't matter whether I is less than j or j is less than I. Any two edge will not satisfy this inequality. Now what that means is, let's say this is the ith edge that is being referred to here. So it says that there wouldn't be an edge which starts after I, so that basically starts anywhere after this and before the end point, right? So there should not be any edge which starts somewhere among these three nodes and go cross the end of the previous edge. So this kind of edge is not feasible at all, right? But notice that they haven't talked about the equal to part. So what this means is this kind of edge is very well feasible. Even this kind of edge is very well feasible. The only thing that is not feasible is any edge starting between these edges and crossing all the way to the end of the, like after the end of the previous edge itself, right? So hope this point is clear, like what this particular thing is telling about. Now it might not make very sense on how this would help us, but let's focus on the next part and it will be very clear. So for now, what we have to understand is there can be edges that can end at same node. There can be edges which can start from the same node and end somewhere afterwards. But if there is an edge already exist, then between any of these nodes you can't have an edge that's go beyond this part. That is, inside this you will have edges like maybe this or maybe this or even this as well, but you can't have an edge that crosses this, right? So that's the basically constraint from this particular statement. So let's come back to the same problem again. Let's say there is just one edge. Now how will you solve the problem if there is just one edge? So if there is just one edge, you can simply say, okay, because this edge will benefit me no matter what, the shortest path will always go through this edge, right? So this will be the shortest path always, right? Because this edge will basically connect two nodes which were greater than one distance apart, right? So in that case, what we are saying is we can simply skip all these nodes altogether and say this is our new graph. But is that feasible? Answer is yes. Answer is no if the constraint was not there. But answer is yes with that constraint. How? I would strongly encourage you to pause and try to think for a moment. So hope you thought about it. Let's first figure out why the answer is no in case that constraint is not there. So if there is no constraint on how the edges would look like, there could be an edge that could start from here and go all the way till here. Very well possible, right? And if that's the case, your shortest path will not follow this route. Instead, it will follow this route because that's even shorter than the previous route, right? In other words, you will have something like this is how your new graph would look like. You can now assume that these are nodes are not there, and instead this is your shortest path. This is how your shortest path look like, right? Now, what this mean? This mean that given any edge, you can't simply go and remove all the nodes in between, because there could be an edge which could start from any of these nodes, and if that edge is starting here, it could benefit more than what the current edge is benefiting from, and you can instead skip this edge altogether and take this edge for the shortest routes, right? This is like in a general graph, but in this case that's not feasible, right? You can't have an edge that starts from somewhere between and crosses the boundary of the previous edge itself. That's the exact same criteria which we discussed a while back, right? So this kind of edges are not at all possible. So if there is an edge like this, we are certain that there will not be any edge like this, and because there will not be any edge that is crossing this boundary, it means there can be edge like this or there can be edges like this, but any of these edge will not matter to us. Why? Because even if these edges are there, you know that you will not be visiting any of these edges. You will simply be visiting this edge and short circuiting this entire nodes fully. In other words, with the given constraint, you can, if there is an edge, you can simply assume that everything between them doesn't exist anymore. And by saying that, basically you have reduced your graph into a simple straight line graph again, and the shortest distance between 0 and n minus 1 would simply be number of nodes between them, right? So again, just to reiterate this part, what we are saying is, for every edge we will simply remove everything between them, every node between them, and we can do that only because we know that any edges that would start or end at those nodes will not be helpful to us at all, because for them to be helpful they need to be better than what the parent edge is giving us, and they can't be better because they can't cross the parent boundary itself. So these edges will be constrained in this full space itself, and hence they can't be of better use, right? So the solution is simply remove all of these and consider this as a new graph, and number of node in this new graph will give you the shortest path between 0 and n minus 1, right? So what's the pseudocode? The pseudocode would simply be this. You can take a initial set of all the nodes from 0 to n minus 1. For each query, you can iterate over all the nodes between the queries and simply remove them from your set. And finally, you can count the number of nodes that is remaining to you, and that minus 1 will be your number of the length of the shortest path between 0 and n minus 1, right? Now, what's the time complexity of this entire algorithm? If you think about it, what you're doing is, for each query you are iterating over n number of things in worst case, and for each you are doing a erase on a set, which will take you log n time again. So the complexity is not better than what we had with the brute force solution itself, but you can optimize this much faster. How? Again, would encourage you to pause and try to think for a moment. So hope you thought about it. So what's the main issue with the current solution? The main issue is you are doing same thing multiple times, right? And because you are doing same thing multiple times, that's where you have this n in the first place. For example, let's say you have this edge. Now at this edge, you will remove these 3 nodes, right? And in that case, the number of node remaining would be 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, and the shortest distance will be 6, right? Now you got one more edge like this. Again, you will try to go and remove all of these, but they are already removed, right? So you will not do anything else. Basically, all of these operations will be your no op. And because it is no op, you still iterated over all those nodes and tried to delete it. So the complexity is still, you are still incurring the cost of all of these, even though they are not no op, and the shortest distance will remain same, which is 6. Now you got one more thing, and in this case again you will try and go and delete all of these, right? Now in this part you will delete some of those, but most of them, like at least half of them is kind of already deleted, but you are again doing a no op operation here. So if you can somehow avoid this no op operations, your complexity would be a lot better. Why? Because what you are doing, if you are avoiding no op operation, basically you are saying that every time I will delete one node for sure, right? And if you are able to achieve that point, then you can't delete more than what you have, right? So you have total n number of nodes, and if you are saying that either I will delete one node or I will not do anything else, so in that case what you are saying is you can go at max n log n time, like you will need at max this many time over all the queries, not in all the queries, rather over all the queries, and that will improve your time complexity, right? Now how to do is, again encourage you to pause and try to think by yourself. So the easiest way to do this is, you can simply, let's say there's a new edge like this, you can simply see what all nodes are remaining in this part, and how you can figure out that using lower bound and upper bound. So what you can say is, okay, I need to delete everything between this and this. So I will figure out the upper bound of this node, which is this, and I will continue deleting everything until I hit this. So what you are saying is either you will delete or you will stop. That's what you're saying, right? So in this case, you will go and delete all these 3 nodes, and you will do log n operation thrice. Like one more log n operation for this, but let's forget about this. So what you're doing is, for every query you are first doing upper bound, and then you are doing x number of iterations, let's say x1 number of iteration, and for each x1 number of iteration you are incurring log n cost, right? So for this particular iteration you incurred x1 log n cost, right? And another log n because you did a lower bound as well. Now let's talk about the second query. So in this query you will again do a log n, like do upper bound, so that incur log n time. So if you do upper bound, this time you will get here. No, sorry, this node doesn't exist, so you will directly get here. Now you will again see whether to delete or not, and this time you will say I don't have to delete anything else because that's my last completely. So in just log n time, you decided to stop your iteration. In other words, the value of xi is 0, or in other words you are saying that you are doing x2 number of iteration, and for each x2 number of iteration you are incurring log n cost. Now again for third query you will do upper bound, that will take you log n time. So if you do upper bound from here, you will directly jump to this node itself, because this node was not deleted before. So at this point you will try to remove this node and then go to the next node, and when you go to the next node you will skip each of these because this node doesn't exist anymore. So you will directly come here and again delete this, and then go to the next node. You will see, okay, this is also something which is between these 2 nodes, so you will delete this one as well, and so on and so forth. So basically you will again do some x3 number of iteration, and that will take you order log n time. Now if you sum up all of these across all of these queries, what you are saying is you are doing log n. First log n is required for every query. So for q number of queries, you are doing log n operation for sure. After that, you are doing log n operation for x1 plus x2 plus x3 all the way up to xn. And this entire thing sums up to n, because you can't do more than n deletions anyways. So this entire thing is n. So overall complexity is q plus n log n, which is sufficient to pass the given time constraint, right? So we had q n log n, and now you are saying that you have q plus n log n, right? So hope this entire thing is clear. Again, just to reiterate, what the entire problem was based on the observation that there can't be any node, any edge that crosses the previous edge fully, or that cuts the previous edge fully. And because of that, you can simply assume that whenever there is an edge, you can simply ignore everything between them. And because you can do that, it's the shortest path calculation is very easy. You just need to figure out what's the number of node between 0 and, or what's the number of nodes remaining between 0 and n minus 1, and that will be your shortest path, right? So if you have watched this point, I would strongly encourage you to pause and try to code this entire thing by yourself. So next, we're looking at the code. The code is exactly what we just discussed. We have this set, we push everything to the set initially. Now for every query, we are simply figuring out its upper bound, and then we build an array which denotes which all numbers to remove. Now why this vector is required, why can't we simply erase here? I would leave that as an exercise to you. You can comment about it in the comment section below so that others can learn from that. But what we are doing simply is we are iterating over the set until we hit the last value, and between them we will push everything to a array which needs to be removed, and finally we iterate over the array and erase everything there. Now after this iteration, the set will contain only the nodes which matters in the given graph, and the number of the distance between the 0 and n minus 1th node would simply be number of nodes minus 1. So we will keep on doing this for every queries, and finally we return the result as an answer. So if you have any doubts, feel free to post that in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one.